Here's part 5. Consider here I of lambda equals 0 to infinity, e to the negative lambda, quantity x to the fourth plus x squared dx, for lambda is much larger than 1. Part A, identify dominant contribution. Part B, expand exponent near stationary point. Part C, derive the leading order asymptotic approximation. Part D, compute the next order correction. And Part E, estimate the error term. So this is asymptotic analysis. We have I of lambda equals, from this integral 0 to infinity, e to the negative lambda, quantity x to the fourth plus x squared dx, where lambda is much larger than 1. So the dominant contribution comes from x equals 0, where x to the fourth plus x squared is minimized. So our scale here, x equals u over the square root of lambda. So then dx equals du over the square root of lambda, and lambda times x squared plus x to the fourth, that equals lambda times that u squared over lambda plus u to the fourth over lambda squared, that equals u squared plus u to the fourth over lambda. So I of lambda equals 1 over lambda, 0 to infinity, e to the negative u squared, e to the negative u to the fourth over lambda du. Expanding, e to the negative u over lambda equals 1 minus u to the fourth over lambda, plus big O of a lambda negative 2. And I of lambda equals 1 over the square root of lambda, bracket integral 0 to infinity, e to the negative u squared du, minus 1 over lambda, 0 to infinity, the integral 0 to infinity, u to the 4, e to the negative u squared du, plus big O here of lambda to the negative 2. Okay, so building on that now, we have the following. The integral 0 to infinity, e to the negative u squared du equals square root of pi over 2. And then the integral from 0 to infinity, u to the fourth, e to the negative u squared du, that equals 3 square root of pi over 8. So I of lambda, that's proportional to, or asymptotic to, square root of pi over 2 square root of lambda, minus 3 square root of pi over 8 lambda to the 3 halves, plus big O of lambda to the negative 5 halves. And I of lambda is asymptotic to the square root of pi over 2 lambda to the 1 half, times the quantity 1 minus 3 over 4 lambda, plus big O of lambda to the negative 2. Okay, so, and moving along to number 10. So solve approximately using regular perturbation methods. Y double prime plus y plus epsilon y cubed equals 0, where 0 is less than epsilon is much less than 1. Subject to y of 0 equals a, and y prime of 0 equals 0. Expand the solution in powers of epsilon, y equals y naught plus epsilon y sub 1 plus epsilon squared y sub 2 plus on and on. Part B, solve equations order by order. Part C, identify the secular terms. Part D, remove secular growth using frequency renormalization. And Part E, derive corrected oscillation frequency to first order. Okay, so this is a perturbation theory problem. So y double prime plus y plus epsilon y cubed equals 0, y of 0 equals a, y prime of 0 equals 0. Our naive expansion, y equals y naught plus epsilon sub 1 plus on and on and on. At order 1, y naught double prime plus y naught equals 0. With initial conditions, y naught equals a cosine t. At order epsilon, y sub 1 double prime plus y sub 1 equals negative y naught cubed. Since y naught cubed equals a cubed cosine cubed t, that equals a cubed over 4 times the quantity 3 cosine t plus 3 cosine t. From there, then we have the following. Y sub 1 double prime plus y sub 1 equals negative a cubed over 4 times the quantity 3 cosine t plus cosine 3t. The cosine t forcing is rested on and produces a secular term. To remove it, we use Lindstedt-Poincaré. Let tau equal omega t. And omega equals 1 plus epsilon omega sub 1 plus on and on. 1 plus omega epsilon omega plus on and on and on. Then omega squared y sub tau tau plus y plus epsilon y cubed equals 0. And we let here y equal y naught plus epsilon y sub 1 plus dot dot dot. At leading order here, y naught double prime plus y naught equals 0. And then, so from here, y naught equals a cosine tau. Order epsilon here, we're going to get y sub 1 double prime plus y sub 1 equals negative y naught cubed minus 2 omega sub 1 y naught double prime. So, sorry, but the omega sub 1. I can't remember if I said omega sub 1 or if I said omega, but omega sub 1. So moving along here, since we have the following y naught double prime equals negative a cosine tau, y sub 1 double prime plus y sub 1 equals negative a cubed cosine cubed tau plus 2 omega sub 1 a cosine tau. So using cosine cubed tau equals 1/4 times the quantity 3 cosine tau plus cosine 3 tau, we're going to get y sub 1 double prime plus y sub 1 equals that quantity 2 omega sub 1a minus 3a cubed over 4 cosine tau minus a cubed over 4 cosine 3 tau. We remove resonance by setting 2 omega sub 1a minus 3a cubed over 4 equal to 0. So we wind up with omega sub 1 equals 3a squared over 8. So the first order corrective frequency is omega equals 1 plus 3/8 is in a squared plus order plus big O epsilon squared. The approximate solution is y of t is approximately a cosine bracket quantity 1 plus 3/8 epsilon a squared t close bracket 2 leading frequency corrected order. So this is the standard hardening Duffing oscillator behavior. Positive epsilon increases the frequency. Okay, so this is all for part 5 and the practice exam. Thank you very much and have a great day.